Good morning, everyone. So today it's my pleasure to introduce you to the latest development of the Copernicus Emergency Management Service, the new feature, the Global Flood Monitoring. I'm Andrea Betterle, and I would like also to acknowledge my co-authors, and in particular all the GFM developing team, which includes university, research institutes, and private companies all across Europe. So disaster risk management and reduction is fundamental in the institutional mission of the European Union. And this calls for reliable source of information that are open source at the global scale and on natural disasters. And this is fundamental to develop policies aimed to tackle natural hazard, both man-made and naturally driven at a global scale, in order to develop a policy to reduce the impacts of these disasters. And in particular, the Copernicus Emergency Management Service follows natural disaster across their entire life cycle, from preparedness and forecast to monitoring until like the impact assessment. And in this context, GFM is focusing on floods, on monitoring floods, at basically on real time, near real time, at 20 meters spatial resolution all across the globe. And this is done by automatically ingesting and processing all Sentinel-1 acquisition for the European Space Agency Sentinel mission. As you can imagine, like such a system offers unprecedented opportunity in the field because it doesn't require any supervision basically, and automatically process all the Sentinel data at the global scale. But it also comes with significant challenges. In fact, looking at such rare events like floods at this scale is a little bit like looking for the needle in the haystack. So briefly, we already heard yesterday about SAR-based flood mapping. SAR is extremely effective in mapping floods, water in general on land surface, because it's an active sensor, so it operates regardless of weather condition, because it can penetrate clouds because it's in microwave frequency, and it's an active sensor, so it can operate both during the day and during night. And furthermore, at this frequency, water appears fairly clearly in general on land, because it's a strong contrast as compared to the surrounding dry land. So the final goal of GFM is turning a raw SAR image, like the one you see on the left, into a classified product where flooded areas are clearly delineated. And this is done by 3 state-of-the-art flood classification algorithm developed by leading European institution in the field of SAR-based flood mapping. So in particular, the German Aerospace Center, the Technical University of Vienna, and the Luxembourg Institute of Technology. GFM works in a so-called ensemble way, so it combines all these 3 algorithms, leveraging all the strength of each of them. In fact, they work in a very different way. So combining all of them allows a more reliable and more robust flood delineation. The key product of GFM is, of course, the delineation of a flooded area, but that's not the only one. It also comes GFM with the delineation of all surface permanent and seasonal water bodies. And an additional layer featuring the union of the previous 2 shows all water on land. Additional output products of GFM include some interesting one, in my opinion. So the so-called exclusion mask, which delineates explicitly all areas that were excluded from mapping because of technical reasons, such as the presence of vegetation or urban areas or radar shadows on ground. And an additional likelihood layer, which provides on a pixel level the confidence of the classification result. GFM also provides many other output products. I'm not going to describe them now into the details, but I invite you to check them out online. And if you ask where can you find GFM, so the first access point is via GLOFASS, and in particular through the monitoring tab of GLOFASS. Here you can display all the output of GFM, also define areas of interest and notification rules. So if a flood basically appear in a user-defined area, the user can receive an automatic notification. All these things are possible also through the dedicated portal GFM, which additionally allows the user to download single products, or it additionally allows to create a special temporal aggregates of GFM products and easily download them locally. This information and many others are available on the rich documentation of GFM, which is available online. So in particular, addressing more the user perspective is the product user manual and the quick start guide, whereas the product definition document describes more into the details, the technical aspects of the system. To conclude this first part of my presentation, I would like to point out some of the improvements that are soon going to be released. In particular, GFM will soon feature an upgraded version of the classification algorithms, which should significantly improve the classification accuracy. We will also include a more an enhanced and less invasive exclusion mask, as well as an updated permanent and seasonal water body layer. And soon, next year, we are planning also to reprocess the entire Sentinel archive from 2015 onward in order to provide flood classification at a global scale in the last decade. So now I would like to move to a second part of the presentation, which is more focused on what I'm currently working on, still using GFM. So GFM is great, but it shares some limitation with other SAR-based flood classification system. And in particular, it struggles to detect water under some condition. And the most critical of which is in presence of urban areas. And this, as you can imagine, is especially critical because that's exactly where we are most interested on. And additionally, GFM provides flood delineation, but doesn't provide any information on flood depth, which is maybe the most critical information, for example, for flood impact assessment or recovery planning. Luckily, as I mentioned before, GFM comes with this exclusion mask, which can be extremely useful because we know exactly where flood mapping was not performed by GFM. So what I'm trying to do now is to combine GFM delineation output with additional external source of information, in particular topographical information in the form of DTM, to enhance flood delineation provided by GFM, and in particular expanding them inside the exclusion mask using simple morphological arguments. And additionally, to provide with the water depth estimates. So the workflow I developed is fairly simple, and it also follows some methods that have already been developed. So to estimate water level inside the flooded area, a very critical location is the point highlighted on the left. So if we have a set of flooded pixel and a set of non-flooded pixel, the point in between the two, if we add the topographical information and we consider a cross-section, it's very important because the water level, in principle, it must be included between the elevation of two neighboring wet, flooded and non-flooded pixels. So identifying these borders is fundamental for water level estimates. So in this set of steps, illustrates how these pixels are identified. So if we start from a setting like this, if we imagine to delay first the flooded area and then eroding it, we can compute the difference between these two areas and we identify the entire perimeter of the flooded area. However, some of these borders are not valid to estimate the reference water level because they are shared with, for example, permanent waters or exclusion mask. So the entire perimeter can be clipped by an additional dilation of these two previous layers to obtain just valid border pixels. And once these borders are identified, if topographical information are included in the form of DTM, it's possible to estimate the reference elevation for these borders and then extrapolate this elevation across the entire flooded area to obtain a water level estimation. Once the water level is estimated inside each flooded area, it's possible to proceed with the further flood propagation routine, which basically propagates flood water inside the exclusion mask as long as the elevation in the exclusion mask is lower of the elevation of the ground is lower than the estimated water level. And to prevent unlimited expansion that can occur under some particular topographical condition, there is an additional routine enforced that progressively reduces water level as distance increases. And water depth, of course, can be simply computed by subtracting from the water level the elevation of the DTM underneath. Again, back to Pakistan, this is the test of the algorithm during the most devastating flood that hit the planet last year. And yeah, we learned already about it before. And from the scale bar, you can see how the magnitude of the event. And if we zoom in more into the details in a small area, we can also appreciate some more aspects. So here you see the comparison between the initial flood delineation provided by GFM in black. And below there is the enhanced version with the flood expansion procedure, which provides a reasonable water depth, and also in particular it allows the identification of likely flooded areas in urban areas, which would not have been captured otherwise by GFM. So in terms of classification accuracy, here I compare the GFM without and with the flood expansion procedure against as a reference, the Copernicus map of an area of interest. The Copernicus map is developed with a semi-automatic procedure with expert knowledge refinement based on optical images. And here you can see the result in terms of true positive, true negatives, and so on. And already the GFM initial output is fairly good. And it's further enhanced with the flood expansion routine, which significantly reduced the number of false negatives. And although it also increases the number of false positive, it's also likely that the reference map suffers from some underestimation. And here you can see also, for completeness, the resulting water depth for this case. So finally, to test the performances of the procedure in terms of water depth estimate, this is a little bit more complicated since usually such ground reference data are not available, especially for a scale like this. So what I did, I took advantage of the NASA satellite ISAT-2, which provides extremely accurate altimetric information along tracks of points. So at a very fine spatial resolution. So luckily there was an acquisition of ISAT in the area, more or less corresponding to the flood peak. And from this data, it's possible to compute two differences. So the first on the top is simply the difference between the ISAT elevation during the flood condition compared to an ISAT acquisition in the same track during a no flooding condition. Whereas the second histogram is the same difference as before, but adding water depth estimate with the procedure I just showed you. And you can see clearly how adding the water level estimate, the water depth estimate, significantly shifted the distribution towards an ideal error of 0. And in particular, also the most frequent value now matches a 0 error, and also both the bias and the variance are significantly decreased. To conclude, so the methodology appears promising for large-scale application because it requires minimum supervision and it runs in fairly low computational times. So it appears indicated to provide flood delineation, including also flood extent enhancement and water depth estimate over large areas all across the globe. Our plan for the future now is to apply this procedure to the entire data set, GFM database from 2015 onwards. And ultimately, our idea would be to come up combining this data with external source of information on exposure, such as like land cover or population affected, come up with some sort of worldwide flood impact database from
over the last 10 years, basically. And with this, I'm done. And in case you have questions, I think I'll go to good times.
Yeah, perfect. Questions?
You conserve active water, and you're going to look at days at the different level, you know, you're going to what
You mean related to the revisit time of the Sentinel?
yeah, look at that at a good time. Years after.
I didn't check it explicitly. I know I read the paper about it. I don't know if it's exactly what you are referring to, that they compare like the likelihood to match a flood peak based on the frequency revisit time of the satellite and based also on the scale of the flood, because that depends a lot on for example, it's really hard for this system to catch flash floods, for example. What happened in Libya recently, there is some delineation by GFM, but it's not as extensive as the actual event. So the larger the scale of the flood, the longer the time and the more likely you are to capture the peak.
Thank you for your presentation.
Thank you.
It's great to see the usefulness I think to LiDAR installations. You also tried dead-eye LiDAR.
No, I didn't.
Did you need a repeat pass?
So yeah, the problem of ISAT is that there's a revisit time of 3 months, basically. So you have to be a little bit lucky. So it also comes with the time scale of the flood. So the bigger it is the flood, the more it remains, and the more likely it is to be kept also with ISAT. And another thing with ISAT is that it's very difficult that it has to find exactly matching tracks, because there's always a little offset with few meters. Actually, the 2 tracks I use have an offset of 50 meters, which it depends. If in a flat topography is not going to affect much, but if it's more rough, it might have an impact. But so yeah, I compare like two overpasses during 2 different periods. Yeah, it's quite simple. So basically, the 2 algorithms out of 3 must agree for a flooded pixel to be delineated as flooded. So if 2 algorithms say 1 pixel is as water and another one says is not flooded, it will be flooded. So it's based on the majority of the 2 out of 3 that must agree. Yeah, there is already. I didn't mention, but maybe it was written on one of the slides. I'm not sure. But there is there are also APIs place. No, I basically defined that it's based on the size of the initial flooded area for which spreading started. So a little bit like a mass conservation principle. So a small flooded area can propagate less further than a big one. So that made it was simple, but made kind of sense to me. But it's not linear, so because otherwise big ones can spread really a lot. So.
All right, thank you so much.